screwed. Okay, so I totally think I totally screwed up the recording. So high energy diffraction microscopy is. Don't worry about writing this down. This is kind of an aside. So basically, what you can think about is there's near field and far field kind of things. But you have a synchrotron source, right? So you've got a giant ring. Say the APS is about 2 miles in circumference, right? And you've got electrons whizzing around that ring at a very sizable fraction of the speed of light. And you accelerate them around that ring with huge bending magnets, right? And every time the electron moves, right, you get a huge amount of X-rays coming off, right? You can use those X-rays for characterization purposes. They go through a monochromator, so you've got a monochromatic beam. And because of the way that they're accelerated, it's approximately coherent. It's not, right, it's not forcibly, it's not coherent in the sense of, like, if you're doing, like, laser, right? But it's more than you would get from a lab source setting. And then, so that, at the APS, the work we were doing most of the time is around 86 keV, right? So very high energy. You can penetrate, whereas a normal, like, lab scale X-ray source, you can go penetrate a couple hundred nanometers into the material. The APS, you can go, say, centimeter thickness through aluminum, right? So there's a couple different techniques. So you can have a small sample, right? That's, say, that you only have a couple hundred grains in here, right? You shine a beam. Right? Here's your detector. You've got a 2D area detector. And basically you get Laue patterns, right? And if you rotate this beam while you're collecting, right, the grains come in and out of position, coincidence, right? And you can collect all the spots from all the grains. Now, if you're doing an in situ compression test, you monitor how those Laue spots shift, right? How they change, and that gives you strain information. But you also have, basically you can think of ray tracing, right? And you can map, you know what the Bragg condition is because you know the orientation. You can then backtrack and figure out where that grain was in your sample, right? So that gives you the full elastic strain tensor in the grain. It also gives you the position of the center of mass of the grain, right? So that's far field HEDM. The near field technique, you've got your same sample, and now you've got a detector very, very close. So you're basically what shows up on your diffraction on your detector is the image of your grain, right? It's the Fourier transform of the grain. So you set a planar beam through, and you collect everything in the near field regime, and then you actually can imagine having 3 detectors, right? I'll get a spot from a grain here, a spot from a grain, a spot here. This is totally an aside. This should have been a 30-second thing, but it's such a cool idea. And then basically you can follow it back to the exact point in that grain, in that position. position. So what you do here, now you have a full 3D spatial map, but you can't get strain information, right? So, but you can get a 3D, it's non-destructive internal structure, right? And then you can compress it and look at how it's changed, right? And things like that. You can also do, in the microscope, you can do cross-correlation electron backscatter diffraction, which is where you compare the Kikuchi patterns to get a relative strain measure between them, right? But it requires you saving all of the Kikuchi patterns from your EBSD detector offline, and then doing a really complicated analysis after the fact, right? So there's techniques that are really being developed to kind of get at a lot of this information. This is what we've always referred to as in the mechanics world as mesoscale, right? And now the rest of the world is catching up and likes that term and basically shut us out of it. But in the solid mechanics world, we've been talking about mesoscale stuff, which is at the level of sub-grain to a handful of grains for 25 years. Okay, so a couple of key ideas here. That I really want to hit today. And so we have right, the big idea is, so say we've got a polycrystal. And we got something like this, right? And macroscopically, right, this is, say this is 500 microns, right, here. Right, these are pretty big grains, right? The stress state here, right, can be drastically different than that's applied macroscopically, right? That's, I think, the first key idea, right, is that this is a really inhomogeneous situation, right? Where does that inhomogeneity arise from? Right? Where does it start?
It's compatibility of the orientation of the grain.
Yeah, so you got orientation of the grains, right? So if you have a material that's highly elastically anisotropic, right? And I put a load here, right? It is not out of the situation. To have a grain, this is a tensile load. I could have regions of the grain here that are seeing a very highly compressive load, right? So it's not just the common picture that people make is, here's my average stress. This is some position, this is stress. Here's my average stress, and I've got fluctuations about this. That picture doesn't hold, right? Really, here's my average stress, and I've got, all over the place. Then once I start deforming, it gets even worse, right? Because in a sense, my deformation is quantized, right? I've got right? I only have a number of potential slip systems here, right? So I have to accommodate an arbitrary deformation by discrete Berger's vector slip lengths on a discrete number of slip systems. Right? And I have to make sure that my stress field is in equilibrium. And I have to make sure that I satisfy compatibility of my deformation field. Right? So this is why polycrystal stuff becomes so difficult. Right?
Not just for one grain, right?
Not just for one grain, right? You can't, and I heard a very respected ceramicist ask a question when someone was talking about high temperature deformation in ceramics. They're like, well, why is polycrystal so hard? Just take it and just average it all together. It doesn't work, right? And this is why. So, how many slip systems do we need to accommodate an arbitrary deformation? It's 5, right? Where does that 5 come from?
Deviatoric strain tensor.
It's deviatoric. So why deviatoric?
Because it's plastic deformation. That's it. No hydrostrain.
Yeah, right. So it all comes back to the fact that hydrostatic pressures won't cause plasticity, right? I can take a hunk of metal and increase the pressure on it, right? And I can just keep increasing the pressure. It's going to deform, right? It's going to deform elastically, right? I have a bulk modulus, right? It's going to change volume, but it won't activate slips. And to a first approximation, right? We have a really complicated heterogeneous system, right? So it is quite possible that if I increase the pressure on my polycrystal aggregate high enough, I'm going to have a stress state here in the middle of this grain, which is not purely hydrostatic, right? The sum of the ensemble stress over all of the grains has to be perfectly, right? But you can imagine taking a single crystal, right? And you hydrostatic. If you take a single crystal and you increase it, you're never going to get flow. So we've got a deformation rate tensor D, right?
If we put pure shear stress, pure shear condition,
Yeah.
then can inside hydrostatic stress state form in polycrystals?
If you a pure shear macroscopically,
Yeah.
You can have if you apply a deformation that is traceless, right? So you can have a stress state here that is triaxial that is not. Right? It does have a hydrostatic component, right? So it works conversely. But we can think about, right? We call within the grain, in the individual grain, the hydrostatic component of stress doesn't matter, right? It's only shear on the given slip systems that matters, right? So we've got a strain rate or deformation rate tensor that is purely deviatoric. So that means there is some reference frame where I can write this as all zeros on the diagonal. Right. So since the diagonal has to sum to 0, means I only have 5 components, independent components of my deformation. Right. So therefore, I need 5. Right. It's just a linear algebra problem. Right. If I have 5, if the rank of my deformation, my mapping is 5, right? Then I need any arbitrary 5 basis vectors, right? As long as they're not collinear, right? I can write that deformation. Does having 5 independent subsystems guarantee that you're going to be able to deform your material?
dislocations and
Yeah,
material stress.
Yeah, you have to be able to move your dislocations, right? Your plasticity carrier, right? So if you don't have significant mobility, you can't overcome the Parles-Navarro barrier without fracturing your material. You're not going to have be able to accommodate. Right? Iridium is right. It's a metal, but it's brittle. Right? It doesn't deform. Right? Ceramics only at high enough temperatures that we can overcome the Parles stress. Right? Okay. So this was stuff figured out a while ago, right? And then basically you had two kind of theories, first order approximations of how to deal with this, right? Taylor and Sachs, right? What did Sachs say?
Singles, everything's same stress.
Same stress, right? Right. We have to maintain stress equilibrium, right? So, right? We have to maintain stress equilibrium. So what's the easiest way to do that? Make all the grains see the same stress, right? If stress is a constant, right? Right. Which means compatibility is violated, right? So you end up opening up holes, right, in your material, right? I mean, conceptually, that if this were true, that's what would happen, right? I would have a stress. Each grain would activate a different slip system, right? And I wouldn't maintain any compatibility at the grain boundaries. Right? What was Taylor's?
Constant strain.
Right? So why did Taylor say constant strain?
Because Sachs, were they derived independently, or?
Yeah. I mean, they were just different theories, right?
Well,
different ideas.
The constant stress assumed like overlapping or gaps in the grain, right?
And you don't see that.
Yeah.
Right? So Taylor said that compatibility is supreme over
stress.
right? So he basically said the strain rate everywhere is a constant. We won't worry about compatibility. It will maintain compatibility. And you know what? Forget equilibrium. Right? So stress equilibrium is not satisfied in the Taylor's theory. Right? And so these are the two, these give you bounds. Right? The real behavior is somewhere in between these. Right? You can show that this corresponds to a rigorous bounds on the behavior, but that's well beyond what we want to do here. So then what happens in a real material, right? So I've got a heterogeneous stress state because it's elastically anisotropic, right? So I'm getting yield somewhere, right? We talked about this in the pileup, right? This grain might yield. I'll start slipping here. I'll get a pileup, right, which will activate a Frank Reed source here, right? And now I might get deformation here, right? So the grains don't all start deforming at the same time, right? And then they don't all deform in the exact same way, right? And we haven't talked about twinning yet, but a real clear evidence of this is how poorly the Schmidt law is followed for twinning, right? You have twins that form that can have negative Schmidt factors, right? Because the local stress state is so drastically different than the macroscopically applied. So you see, if you look at slip traces, the slip trace that you observe is not necessarily the one that you're going to see that is, right? And it doesn't have to be constant across the whole grain. Okay, so now let's get into the confusing part, right? This is really what I want to hit on. So, okay, so this idea, Taylor's idea of minimum work, right? Does anyone want to take a stab at, right? Just throw back at me what you understood from the lecture, with the understanding that it's probably going to be completely off base.
Well, for it being work, wouldn't it be that that the strain rate sort of has to do with sort of, I don't know, there was a term of strain rate.
So, okay, so what we have is we have a given, we've got a given strain rate, right? This is given, and we're looking for the shear rates on all of the different slip systems that make up, that will give us that strain rate. Right? These are our unknowns. Right? So for FCC, I've got 12 of these. Right? And I'm trying to find the combination of the 12 that gives me the strain rate. Right? Why is this a problem? Right? Mathematically, it's an overdetermined system. Right? For FCC, I've got 12 of these. Right? And I've got 5 components here. Right? There's an infinite number of ways I can assign my shear rates to my slip systems to give me this deformation, right? So Taylor invokes, well, the one that's going to work is the one that's going to be operative is the one that's going to take the least amount of energy, right? Nature's not going to go above and beyond what it needs to, right? It's not going to do more shear that counteracts itself to get a given deformation, right? And so it's a really simple idea, right? We do the least amount of work possible. Okay. So in FCC, what are our assumptions? Well, we've got 12 slip systems. The assumption is that the critically resolved shear stress on all of these 12 systems is the same. The rate of change on all of these systems is the same. Right? So they all harden uniformly. Right? And if this is the case, right, and we just think about work as force times distance, right? Then the minimum amount of the force is going to be the same on all the slip systems. So the minimum work becomes the minimum shear. So what Taylor says is an FCC is the way to break this up is to find the shears that give you the minimum amount of total slip activity to match your applied strain rate, right, or your applied deformation. Right? So the minimum work for FCC is the minimum shear. What about for other slip systems? What about BCC?
Doesn't that get a little more complicated?
It gets a heck of a lot more complicated because we've got a lot more slip systems. And is the critically resolved shear stress on all those subsystems the same?
No.
No. Right? So in that case, you need to, it's still going to be the one that gives you the minimum
work.
The minimum
You
work,
can't simplify it to minimum shear.
but you can't simplify it to minimum shear. Right? Same thing for HCP. Right? Or anything other than FCC, basically. Right? Okay, so that's the minimum work idea.
Is that why they always do this with nickel? With the single versus double?
Yeah. And a lot of this, the motivation for this was actually industrial. A lot of this, the theory and the application of crystal plasticity models was driven by beer cans. Right? And I'll talk about this a little bit on Wednesday, but the need to make better and cheaper beer cans, like thinner walls. What you get is if you go through a series of stamping operations, and you have the top of the can, and because of the texture, you get what's called earring. The top of this isn't flat, right? And so you have to trim this off, right? And this is material that's gone through a lot of processing already. So this is removing a lot of value added, right? So if you could save money by processing your sheet in such a way that this didn't happen, right? Okay, so that's the minimum work, right? That's hopefully pretty straightforward, right? There's a lot more detail in the notes. But what I want to do now, now we go on to this seemingly contradictory statement, right? We said we have the minimum work principle, and now we have maximum work, right? And that they're equivalent to each other, right? This takes a little bit of getting used to. Okay, so what did minimum work? What was our given for minimum work?
Shear.
We're given a macroscopic deformation, and we're trying to find the shear, the shear. What maximum work is saying is we want to find the operative stress state, right? Under minimum shear, we didn't talk about stress at all, other than PD, right? Than computing the work, the force times distance work, right? So here we're given a rate, and I want to find the stress state. Right? So how do I maximize the work being done? Right? So imagine I've got a block on a surface with friction, right? And I want to slide this block on the surface, right? Which force vector, A or B, is going to maximize the work? B is going to maximize the force I need to do the work, right? But right? Because work is force F distance. It's the dot product, right? So if I make the vectors parallel, right? Most of my force is going into, right? It's the same thing, right? If I stand still holding a heavy load, I'm doing no work. Right? On the box, my muscles and everything are doing work, but I'm doing no work on the heavy box. Right? This is the same thing. Right? Basically, the whole maximum work principle comes down to is that the operative stress state is going to be the one that's most closely aligned information that I'm applying. All right, that's the key idea behind the maximum work principle. Right? Okay. Now, why is this useful? Well, it turns out Bishop and Hill did a lot of math, and they figured out that there's only 28 possible stress states in within a grain in a polycrystal if for a given strain rate. Right? There's a small number of possible stress states. Right? So now the problem is reduced to, if I assume that Taylor's theory is correct and the strain rate is constant for everywhere, all I have to do is for each grain, check this list of 28 possible stress states, find the one that maximizes the work, right? And then from that, if I know what the stress state is, I can figure out what slip systems are going to be active. Right? So Bishop Hill gives you a table, right? In the homework to do the Bishop Hill problem, I'll give you the grain orientation, right? You find the orientation, you find the stress, the strain in that crystal with respect to the crystal axes, right? Then look it up on the table, right? Go through all. You actually have to do 56. So you got to think about plus and minus, right? Right. You can have positive or negative, and then that tells you what slip systems are going to be active. And it turns out, if you do this, you end up with either 6 or 8 subsystems that are going to be active in every possible grain, depending on how symmetric your orientation is. Right? So, on Wednesday, we'll work through the problem, through the examples. But in the notes, I kind of give pseudocode of how to go through it, the step by step, right? You've got the orientation. You've got our grain orientation. You need to use that to transform the strain rate into the crystal frame. Then you go through each of the stress states. Right. You go through and you calculate the work. Right. Find the max. And then that tells you which stress state is going to be operative. You can then go to the table, right, and see which slip systems are going to be active. Right? So we're still missing something here, though. Right? How many slip systems do I need to define for an arbitrary deformation? 5. Right? From Bishop and Hill, how many slip systems are going to be active? 6 or 8. So I'm still overdetermined. Right? What this, when I say simple, right, compared to other approaches, right, what this doesn't allow me to do is determine uniquely the shear rates on those active slip systems. For that, I need to use another model. Right, because there's still an infinite number of ways I can break up the shear rates on 8 slip systems to give me So that's the big main ideas from this polycrystal thing, right? So I've got minimum work and maximum work that are equivalent. Minimum work just says if I have a given deformation, I want to find the way of breaking it up that gives me the least total amount of deformation that I have to do, right? Maximum work says I'm given the rate, I'm trying to find the stress state. I want to, the one that's going to maximize the work is that the stress state is most closely aligned with the shear rate, with the deformation rate. Right, that's going to maximize the amount of work that I've done. And when you really get down to the details, they're equivalent with each other. They're equivalent to each other. Right. Along with the general idea of Sachs and Taylor, right? Those are the big ideas for polycrystals that I want to get across. Right? The details are good as homework exercises. Right? Are you going to see a Taylor, Bishop Hill, right, on the calculation section of an exam? No. Right? It's pointless. Right? It doesn't show any kind of understanding. So don't worry about that kind of stuff. We have just a couple minutes, and I wanted to throw out two things. I didn't go over the rotations during single slip and things like that, because I felt that was pretty straightforward. What did you guys feel? Thinking about how the grains rotated and identification of the slip systems. Is everyone comfortable enough with the stereographic triangle to... Someone who doesn't have materials as their undergrad? Was that anyone's first run-in with the stereographic projection? Okay, so we can talk about that. So before we leave today, a couple things. This week I will be posting a set of project problems. Right? This will be due at the end of the term, and it will involve running a crystal plasticity solver, right? And comparing it against Sachs and Taylor, right? To see how it comes up, and doing some things like plotting stress strain curves, right? And just kind of using data from a model, right? Extracting data from a model and running it. So those files and everything will be posted to Carmen, and next week we'll talk about that, right? It's really not a huge deal. It's a couple hours. It counts. This should be a couple hours worth of work, and it basically counts the same as the midterm on the syllabus. Right? The other thing we have to talk about is the final. So I had an idea. It might be a bad idea. I've had one person tell me it's a bad idea already. Right? I was thinking, instead of a written exam, how would you guys feel about an oral exam? Okay, well that's pretty decisive. Okay, then we won't entertain that idea anymore. I thought it might be. It'd be good practice for candidacy.
Yeah.
Well, thanks for asking.
Okay. No, I thought sense in bringing that up again.
We basically have 20 years of written exam. I don't think any of us have taken an oral exam before.
Okay, well, it's a good chance to like just
No,
kind of
I've had
chat.
one small one. But Spanish class.
So the idea of just hanging out in my office for half an hour with a whiteboard doesn't appeal. Okay. I thought maybe, just maybe.
Majority rules.
Well, no, it would be a change for the syllabus, right? So that would mean unanimous agreement. Right. And that's pretty clear that.
You could offer a choice.
Maybe, right? If I offered a choice, would anyone consider it? Okay, so that is, I think, pretty much what we've got today. So Wednesday we're going to work through homework problems, and I will do a little bit with the stereographic projection things. The plasticity in amorphous and semicrystalline materials lectures will be posted, and then on Wednesday we will decide the topics for kind of the remaining terms. So we'll have high temperature deformation, creep in crystalline and non-crystalline. Right, that'll be a topic, but then we can there'll be a bunch of other topics that we can use for the last couple weeks. I think either be composites. I know we'll have a lot of votes for deformation of soft materials. Right, but we can do cellular solids or foams and things like that as well.
Can we do cover twinning or a little bit on twinning?
Yeah, so that's one of the ones. So shear transformations, so
Yeah.
twinning and martensite.
I would love that.
Right. There's also we can do constitutive modeling. Right. How do we develop a constitutive model? Or in previous years, I had a class that had a whole bunch of functional people, and they wanted like higher order stuff, like all the weird cross terms, like the thermomagnetorestriction tensor stuff, and second order elasticity and stuff like that. So it basically goes by the makeup. So okay, so think about it, and on Wednesday or maybe we'll have a Carmen. Everyone votes anonymously kind of thing. Okay.